All right, so problem of the day 5 involved tautomerization. And yesterday we covered acid catalyzed tautomerization. And this is closely related to that. So I'm going to abbreviate this just to save some space. I'm going to call this R, and I'm going to call this R prime. There we go. You guys are welcome to do that too. Just make sure I can follow what you're doing. We've got an OH over here, and we've got our R prime over here. And now we've got this hydronium ion over here. And what was the first step typically? Yeah, there's a couple ways you could show this, but let's do it the way I showed you yesterday, where that double bond can reach over and attack. When you do this, you form, a carbocation down there, and we've got this lone pair here. What's next? Resonance. So let me go back and make sure I've got all my lone pairs in here. We can take one of these lone pairs, we can dump it down, and we can form a resonance structure. Which is pretty nice because now we're at the ketone, so we're halfway there. So in class I told you guys that normally the keto-enol tautomerization favors the ketone side of the equilibrium. In this case, we're going to go back to the enol on one side. Does anybody have an idea why we might? What's that? If I told you, yeah. What did I tell you guys?
You told us that it's kind of like it's just as likely to be on either oxygen, so it happens just as often, but there's a hydrogen bond.
Exactly. So if we look at this, we've got a diketone, it looks pretty stable, but if we look at our final product, there's a couple features going on. We've got alternating double, single, double bonds. We're going to cover this later on this term. This is called conjugation. Conjugation stabilizes molecules. Molecules really like that alternating double, single bond alternation. And if you look at this hydrogen on the alcohol, that hydrogen can hydrogen bond to the ketone, and that stabilizes it. So this is an unusual example where the ketone is not actually the favorable component of the equilibrium. The next step we're going to do is we're going to protonate our other side. So now this ketone will grab a proton. And again, we've got some resonance that we can take advantage of. So I'm going to draw a resonance structure for this, where we can take this pi bond and we can move it up. Now we've got two lone pairs up here, and we've got a carbocation. And what do you think the last step is? Elimination. It looks just like a reaction we saw last term, where we've got beta protons right next to a carbocation. We've got a weak base, that's water. So this water can actually grab one of these beta protons, clamp down, and we go back to our enol. The reality is, it's not a one-way arrow for these keto-enol tautomerizations. It's constantly flipping back and forth in solution, and oftentimes you'll see multiple components all in solution at the same time. This is a really interesting experiment too that you can run in different solvents. And I saw some of you on the problem of the day actually had it condensed down into fewer steps with a highly resonant stabilized intermediate. That's also an acceptable pathway. So there's not one right answer for this problem, but I wanted to get you guys thinking outside the box a little with tautomerization. So let's go back to our notes on chapter 9. Chapter 10, thank you. We can go back to chapter 9, I guess. And we've got a warm-up problem. Oop. All right, this first alkene looks like this. And I'm going to use acid and water. And is this enough to do the hydration? Not quite. We need a catalyst, remember? Alkynes have a really high activation energy for hydration. So what's the catalyst that we use for alkynes? Yeah, mercury sulfate, so HgSO4. All right, and what will our final product look like? What do you guys think? So I'll let you guys think about this for a second. We're doing something that's reminiscent of Markovnikov addition like we saw with alkenes. Is there a Markovnikov side to this alkene or alkyne? No. So we've kind of got ourselves in a conundrum here. We could say, all right, we could have the alcohol come off this side, or we could have it come off the other side, but does it really matter? No, it gives you the same product. And then, if you remember, we've got this tautomerization from our enol to our ketone. Another way to keep track of things is to number it. So you can say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And make sure you don't lose any carbons during this process. Does that make sense? It doesn't matter whether or not that ketone was delivered to that third carbon or fourth carbon. It gives you the exact same product.
How did you get the second one?
This enol?
Yeah, the second one. The one I need.
4, 5, 6.
The other one, the one.
On the right side? This one? So this is a acid catalyzed tautomerization. So just like we saw in the problem of the day, you can protonate that alkene and do all the proton transfers to go from your enol to your ketone. So I'm not going to show that full mechanism, but I do want you guys to remember that it favors that ketone side. All right, I've got another one for you. This time I've got one that looks pretty similar. And again, we're going to use acid and water and mercury sulfate. And I want us to try to figure out what our product or products would be. Is there a Markovnikov side? Not really. It's still an internal alkyne. You can only ever have one other substituent coming off the end of an alkyne. So there's not really a Markovnikov side. So do you think we're going to get one product or a mixture of products? Mixture of products, exactly. So if we look at this, we can number it again, and we can say 1, 2, 3, 4, 5. We could have a ketone coming off of that 2 carbon or the 3 carbon. So 1, 2, 3, 4, 5 plus this ketone. So the main takeaway is that with unsymmetric ketones, unsymmetric alkynes, I'm not spelling right. You get a mixture of products. Typically, people avoid this by always using symmetric alkynes, but occasionally you'll see problems in the book where they use an unsymmetric alkyne.
And the reason it doesn't prefer one side over the other is because there's not a carbocation intermediate.
Yeah, we didn't really cover the mechanism with the catalyst, but in this case, if you look at this side right here versus that side right there, they each have one carbon coming off of them, so they're equally substituted. The length of the chain has minimal impact. So in this case, you could have that carbonyl coming off of the carbon in the 2 position or in the 3 position.
Okay.
So acid catalyzed hydration, we are always doing a Markovnikov-like addition, with the exception of the cases where we get mixed products. Yep.
In the previous example, why is it that the 2 ethyl groups didn't come off as trans as opposed to cis?
In fact, you probably would get a mixture, but it's always going to tautomerize the ketone, so it doesn't really matter too much. That's a good question. So in all of these examples, we're focusing on Markovnikov type addition. However, we can get anti-Markovnikov addition through a hydroboration reaction, just like we saw with alkenes. So you can see a lot of these themes are repeating themselves. So let's review our alkene chemistry. Let's say we have this alkene, and I want to get Markovnikov hydration, meaning I want the alcohol to come off of the less substituted side of the alkene. What reagents do I need? We need peroxide, so that's H2O2. What else? Yeah, first step is that borane complex, so BH3 usually complex to some sort of ether like THF. And do we only use hydrogen peroxide in the second step? Sodium hydroxide. And by doing this, we're able to get anti-Markovnikov hydration. Alkynes are very similar. So let's put down an example alkyne. This time I've got a hydrogen off the end, so it's a terminal alkyne. We can use a borane followed by hydrogen peroxide and sodium hydroxide. And we've got 2 carbons to look at. We've got the carbon in green and we've got the carbon in red. Which carbon do you think is going to end up with an alcohol coming off of it? The red one. It's the anti-Markovnikov side. So we can go ahead and we can draw our enol. Let me clean this up a little. And we've got a hydrogen right there. But now we've got to do a tautomerization under basic conditions. So this is a little bit different than what we saw yesterday with our acid catalyzed hydration. And let me actually show the bond between this oxygen and hydrogen. The first thing we're going to do is we're going to use the hydroxide that's floating around in the second step. What do you think that hydroxide is going to do? Yeah, it's a decent base, so we might have an equilibrium where it deprotonates an alcohol on our enol. Now we've got this oxygen with a negative charge. Does this have any resonance? Yeah. All right, so let's draw the resonance structure for this. This lone pair could dump down, and am I done? No, we would have a Texas carbon at that point, so we've got to break a pi bond. So I'll move this pi bond over there. Now we've got a carbonyl that's formed. We've got our hydrogen over here. Got a lone pair on this carbon, which means it's got a negative charge. And we've got this methyl group. All right, we've created water in this process. Water can act as an acid or a base. In this case, do you think it's going to donate a proton or take a proton? So let's think about it. The intermediate that we have drawn has a negative charge. Is that going to act as an acid or a base? It's going to act as a base. So it's going to take the proton from water, dump the electrons onto oxygen. Now we've got our base regenerated. And we've got our final product. What sort of functional group does our final product have? Aldehyde. So this time, instead of forming ketones, we're going to be forming aldehydes. So anytime you see an aldehyde in this chapter, you can think of the hydroboration oxidation mechanism. Or if you see it from chapter 9, what sort of mechanism gives you aldehydes from chapter 9? Ozonolysis. So now we've got two different ways that we can use to make aldehydes. So in this case, this is called base catalyzed tautomerization. And in this case, it's exclusively going to give you an aldehyde. So let's go back to our reagent really quick, because I kind of sped through this. And I had R2BH. I didn't use borane. Anybody have an idea why I used something that was bigger than borane? Any guesses? Well, let's think about our intermediate. We've got an alkene or an enol in our intermediate. What would happen if we had borane and an alkene? We could get hydroboration again. So the problem with borane is it will add across alkynes and alkenes. So instead, we end up using a really, really bulky borane that can only add across once. It won't add into the alkene at all. And I'll show you guys what this borane is, but oftentimes you'll see it abbreviated in your book or in my lecture notes as R2BH. So let's go down and cover some of those catalysts. The first one looks kind of crazy. We've got groups coming down there and a hydrogen coming off the boron. So you can see it's very, very bulky. This is called diisoamyl borane. And the main thing to be concerned with is these are too bulky to react with alkenes. They physically take up too much space. The other reagent that's really common, and you'll see quite a bit in your book, is a bicyclic borane. And let's see if I can draw this on the first shot. Oh, let me clean this up a bit. And I'll kind of bold in where the carbons are. Let's try to name this using our bicyclic naming system. What's our longest bridge? Not quite. We don't count the bridge head. 3. So if we go through and number it, we could say, all right, we can go through either way, and we could say 3, 4, 5, go around even more. We'd say 6, 7, 8, 9. And if we try to name this,
This is not carbon. Do we have to include it?
yep, you include everything in the ring. And to account for that boron in the 9 position, we called this 9-bora bicyclo. And what should go in the brackets? 331. So one bridge is 3 carbons long, the other one's 3 carbons long, and then the other one is 1 boron long. And we call this a nonane. We don't have to name the hydrogen at all because we're assuming hydrogens through the whole molecule. So you can see 9-bora bicyclo 331 nonane doesn't quite flow off the tongue very well. So oftentimes what people call this is 9-BBN. This is what you'll most commonly see it referred to as, is just 9-BBN. Yep.
Why does the bulkiness allow it to react with alkynes but not alkenes?
Alkynes are inherently more reactive than alkenes because they've got such a huge amount of p-lobes available. Once you get down to the alkene, these are too bulky to borylate your alkene. Yeah. So let's even make a note of that. They're too bulky to work with alkenes or enols, but they do work with alkynes. All right, so let's take some example problems here and practice using this. The first example problem I have uses a cyclohexane derivative. And I'm going to use 9-BBN hydrogen peroxide and sodium hydroxide. And I want you guys to help me predict what should go in our quiz box here. I'm going to make this worth 4 points. It's anti-Markovnikov, right? Again, that trick I gave you with peroxides holds true with the Alkene chapter, which is pretty handy. So again, we have to look at our carbons. We could say, is it going to react with that blue carbon or the red carbon? Red. So what will that red carbon end up as? After tautomerization, what will it end up as? An aldehyde. So again, what you can do is number, because I found students regularly forget carbons when they do this. So we've got our cyclohexane. We've got 3 carbons coming off. So 1, 2, 3. And then we've got our aldehyde, right? So 1, 2, and 3. I don't expect you guys to show the whole mechanism for the hydroboration oxidation, but I do expect you to know how to do the tautomerization step with the base. Whether or not that's base catalyzed or acid catalyzed tautomerization, I do expect you to know those mechanisms. Let's do another one.
Do you have to include the H?
Yeah, try to include the H's off of aldehydes. It makes it a lot easier for me to be able to tell what you're trying to draw. All right, let's do a different one. This time I'm going to give you the product, but not the starting material. Oh, let me make this box bigger. So again, another 4-point question. R2BH. We'll use hydrogen peroxide and sodium hydroxide. What would the starting material look like? So let's number it. We're starting with an alkyne. Which carbon will the alkyne be between? Between 5 and 6. So these really aren't that bad once you get used to them. So that's 1, 2, 3, 4, 5, 6. And let's double check by numbering. We'll go 1, 2, 3, 4, 5, 6. One pet peeve of mine, I'll show you guys. People will say 1, 2, 3, 4, 5. Is that okay? Yeah, exactly. Remember that SP bonds always want to be 180 degrees, so you don't want to show it using that zigzag notation. Try to make sure that you're clearly showing the angles at approximately 180 degrees. All right, so let's quickly summarize the difference between these two, because this is a very valuable synthetic tool, and I'll just give us a generic starting material. We'll use phenylacetylene. We've got two different routes. First one is with acid. Usually we use sulfuric acid and water, so H2SO4, and then mercury sulfate. Second one is the anti-Markovnikov, where we use a bulky borane, followed by hydrogen peroxide and sodium hydroxide. And we get two different products. The first one is similar to Markovnikov, and the second one is similar to anti-Markovnikov. So it looks pretty similar to the Alkene chapter, with the one caveat of that taumerization step in between your enol and your ketone or aldehyde. Make sense? All right. So now we've got to do halogenation with alkynes, which is pretty similar, so it's not going to be too earth-shattering for you guys. Want me to go back? Yeah. All right, sorry. Sometimes I get carried away. Just yell at me if I go fast. Sometimes I even color code these just to keep track. Okay, if I flip ahead? Yeah. All right. So let's go to halogenation. And let's briefly review alkene halogenation. What happens if I add Br2 to an alkene? Will it be syn addition or anti addition? Anti. In this case, it doesn't really matter because that terminal one's not going to have a stereocenter. But we would end up with a mixture of enantiomers in this case. You could have one bromine going back or the other one going forward. All right, let's take a look at what happens with alkynes. What's going on back there? All right, this time we're going to use bromine, so Br2. And we're going to use carbon tetrachloride. Carbon tetrachloride is not used in very many reactions because it's pretty bad for the environment and it's known to cause cancer. However, in this reaction, you have to use it. It's one of the only reactions where you're kind of stuck with using carbon tetrachloride. The mechanism for this isn't super well understood, but you do end up with what you would expect. Your major product will be the bromines adding across in an anti-fashion. However, there actually is a little bit of the syn product. So this doesn't go through the traditional bromonium ion intermediate, and in fact, there's still debate as to what the actual mechanism is. Either way, what do you think happens if we treat this with even more bromine? Yeah, you can go to an alkane. You can brominate the alkene that you just formed and get more bromines added across that double bond. So if you do this, you only get one product. And you end up with 4 bromines coming off of an alkane. So oftentimes chemists will purposely overshoot. That way they can get 4 bromines added across their triple bond. The nice thing with this mechanism is because it's not well understood, I'm not going to force you to learn it. So you just need to remember the reaction outcome for this. Sound good? All right, what was another reaction we used with alkenes that we haven't covered yet? Does anybody have one that they remember from chapter 9? Ozonolysis, right? So now the question is, what happens if we try to do ozonolysis with alkynes? So let's briefly review our alkene ozonolysis. And let's say I'm starting with this alkene. I'm going to treat it with ozone, followed by zinc and water reduction. What will my final product look like? Give you a hint. Will it be a ketone or aldehyde? Aldehyde, because we've got the hydrogens coming off of that alkene. So you'd have one aldehyde here and the other aldehyde over there. So ozonolysis of alkenes always gives you ketones or aldehydes. It depends on what your starting alkene is. With alkynes, it's a little bit different. So let's pick a generic alkyne. Actually, let me color code these carbons. We'll use a blue carbon and a red carbon and a hydrogen. And again, we're going to treat this first with ozone, followed by zinc and water. Actually, I take that back. For these, you only need water to break them apart. You don't need a reducing agent. And again, we're going to cleave this pi bond. But this time, we're kind of in a conundrum. We're not going to get an aldehyde or a ketone. We're actually going to over-oxidize it to a carboxylic acid. So carboxylic acid. And then that red carbon, what do you think it might become if we over-oxidize one carbon? Give you a hint, it causes global warming. CO2. So this red carbon, if it's over-oxidized, will be cleaved off and form carbon dioxide. So this reaction will actually bubble if it occurred correctly. Just like with alkenes, I'm not going to expect you to do the overall ozonolysis mechanism. If you want, you can look at it in your book, but it's kind of steppy and it goes through some funky looking rings. I'm mostly concerned with you guys knowing the overall organic transformation, that when you treat an alkyne with ozone and then quench it with water, you get a carboxylic acid, and sometimes you end up with carbon dioxide if you're dealing with a terminal alkyne.
So if you had an internal alkyne, would you just have 2 carboxylic acids?
Ah, yes, exactly. So you're segueing into my next question. I'm going to show you guys a fun-looking molecule. Actually, let me, there we go. A lot of people said you couldn't make this. You can make this. So alkynes prefer to be at 180 degree angles, but in this case we've got a highly strained alkyne. They've actually gone so far as making the 7-membered ring version of this. But this is called cyclooctane, and it's really popular for click chemistry. So the click chemistry lab that we are doing this week involves an alkyne and an azide, and what was the catalyst we used? Copper, right? So copper will catalyze a click reaction. However, if you strain an alkyne and make it really, really unhappy, it will work without the copper. So this was a new development in the past 10 years with click chemistry. And let's predict what our product will be if we treat this with ozone followed by water. Try to number your carbons.
We go to not other direction.
You can number it any way you want. I just want you to keep track of your carbons. We're not using the numbering for naming.
Okay.
So raise your hand if you think you got it. A few people? Brandon, do you have an idea of what the functional group should look like on the final product? Yeah, dicarboxylic acid, exactly. So it'll be a long chain, 8 carbons long. So 2, 4, 6, 8. And we'll have a carboxylic acid at each end. So we can use this to do a ring opening on highly strained alkynes. 6, 7, 8. The key is to not add or subtract carbons from your product. All right, let's do another one. I'll scroll up here. We're going to treat this with ozone followed by water. I also have a question I want to ask you guys. Is this 4-methyl 2-pentyne? Oop. Or is it 2-methyl 3-pentyne? Which one do you think it is? Top or bottom? Top. Remember, when you're numbering for alkenes or alkynes, you always want that alkyne to be in the lowest position. So in this case, this would be the correct name for our starting material. All right, so do we get one product out of this? Multiple products? 2 products? What do you guys think? 2. And again, we're going to get a carboxylic acid. Let's number everything. Oop. And what I'm going to do is do a 2-carbon chain over here, and that becomes a carboxylic acid. So that's carbon 1 and carbon 2. Carbon 1 we said is a CH3 group. And then we also end up with another carboxylic acid that accounts for carbons 3, 4, and 5. So this would be carbon 3, 4, and 5, and we've got a methyl group coming off of that 4 position. So in this case, if we are dealing with unsymmetric alkynes, we do get 2 different products out. Yep.
Oh, wait, never mind. You just answered my question.
All right. All right, the last thing we're going to cover today is alkylation reactions, but you guys already know how to do this. So let's say I've got my alkyne and I treat it with a base. What will happen? We said that this has a pKa of 25, so if we use a strong enough base, the base is just going to grab that proton and we're going to form our acetylide ion. So we call this an acetylide ion. The cool thing with an acetylide ion is that these are good nucleophiles. So let's imagine now that I treat it with, let's just make up something here. Bromoethane. What do you think might happen if we treat an acetylide ion with bromoethane? Give you a hint, bromoethane's a primary electrophile. We've got a good nucleophile. What was it? SN2, exactly. So this is why we can't forget first term stuff. We can get an SN2 reaction where this acetylide will do a backside attack and kick off this bromine. And now we've formed an internal alkyne. The key for these reactions is you must use a strong base, just like we saw in the problem of the day. Sodium hydroxide, potassium terbutoxide, those are not strong enough. So examples of bases that you can use are sodium amide, so NaNH2. You can use sodium hydride. What's another one we could use? Think back to your pod. Yeah, butyl lithium. So people will just say BULI. That one works really well. There's also another one called LDA. That looks like this. That nitrogen has a negative charge and the lithium's positive. This is lithium diisopropyl amide. And most people just refer to this as LDA. All 5 of these are acceptable bases for deprotonating a terminal alkyne. The other thing to consider is our electrophile. So the electrophile I used was bromoethane. We said that's a primary electrophile. We said we're doing an SN2 reaction. Will a tertiary electrophile work in this case? What do you guys think? No. As we saw with SN2 chemistry, SN2 reactions only work when that backside is accessible. If it's a tertiary carbon, you're not going to get an SN2 reaction. So you must use a methyl halide or a primary halide. Tertiary halides are too hindered. What happens with secondary alkyl halides? What do you guys think? You get a mixture. What's the competing reaction with secondary alkyl halides and good nucleophiles that are also good bases? Exactly. Secondary alkyl halides favor E2. So in this case, we always want to use methyl halide or primary alkyl halide. All right, tomorrow will be a synthesis day. So come prepared to do synthesis problems, and we're going to do small group activities along with it.
How far in the book are we? What section? Did we finish
We're pretty much done with chapter 10. We're going to do synthesis tomorrow, which is also a section in chapter 10, but it's fairly intuitive.
Okay.